So the prime factorization, this is breaking a number into its prime so that everything is a power of a number. So for example, if we had 50 and we broke it apart, then we would break this. We know this is 10 times 5. 5 is already prime. 10 is not prime. So we're going to break that into 2 and 5. So then we could rewrite 50 as 2 times 5 times 5, or 2 times 5 squared, because there are two 5s. Okay, so we're going to do this with the example that we used before. 162. Okay, so we notice it's even, so we pull out a 2. So then using a calculator, when we pull that out, we get 81. Okay, 81 is composite, so we want to split that up, so that's 9 and 9. Okay, and then 9 is 3 times 3. Okay, so that means 162 would be 2 times 81, that's what we did. Or we said 2 times 9 times 9, or 2 times 3 times 3 times 3 times 3. So we have 162, its prime factorization would be 2 times 3 to the 4th, because it's 1, 2, 3, 4 3's. This would be our prime factorization. Okay, so what this technique is called, this is called a factor tree, and that's how we figure out all the factors. Okay, so there's another technique for this factoring business, that what it does is it goes, you check all the factors up to the square root of the number. So if we took the square root of 50, it should be about 7.1, because remember that the square root of 49 is 7. Okay, so this is going to be about 7. So that means if we wanted to find all the factors of 50, we would pair them up just like we were doing before, but we would only have to go up to 7, because once we hit this, this is like our halfway point. So we know we'd have 1 times 50, 2 times 25, 5 plus 0 is 5, that's not divisible by 3, so 3's out. When we took a 2 out, we got 25, so 4's out. 5 times 10, okay, then we try, so we tried 3 and 4 and they didn't work. Then we try 6. 6 won't work because 3 didn't work. So then we can try 7, but 7 won't work because right next to it was a 7. So that means that we've now tried all the numbers, so that these would be all the divisors of 50. Okay, so that's just another technique. So if you're ever stuck on a number like this, you can do it this way. So it's like 162 in the same method. So we're going to do square root of 162. Okay, now the square root of 169 is 13, so this should be about 12.8-ish, okay, somewhere in there. You can use a calculator to get the right idea, but the big idea is that it's going to be between 12 and 13. Okay, so that means we check all of those. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, because we only go up to the square root. So because the square root is between 12 and 13, we only have to go up to 12 when we're done. So 1 times 162. Okay, 2 times 81. If we pull a 3 out of 162, 162 divided by 3, just doing this on a calculator. Whoops. We get 54. So 3 times 54. 4 we already said wasn't going to work because 81 isn't even. 5 won't work because it doesn't end in a 5. We should get something for 6. So 162 divided by 6 gives us 27. 7 shouldn't work, but we can double check it. 162 divided by 7 gives us 23.14, so that's out. 8 won't work because 4 didn't work. 9 should work, so when we do 9, 162 divided by 9, we get 18. Okay, 10 won't work, it doesn't end in a 0. 11, if we do 1 plus 2, we got 3, right? We said 11 wasn't divisible, so then we could try 12. 162 divided by 12 on a calculator. We get 13.5, so that means that doesn't work either. So these would be all of our dividers. All of our divisors right here. Okay, so then our divisors would be 1, 162, 2, 81, 3, 54, 6, 27, 9, and then 18 would be all the divisors. Okay, so then the divisors of 162 would be this, but the prime factorization looks like this. So how these are connected is 162 is 2 times 3 to the 4th, right? It's using all the factors. Here we pulled out a 2, so then we're left with 81. 81 is 3 to the 4th. You can confirm that on your calculator, right? If we take out a 3, then 3 of the 3's would be left and 1 of the 2's. That should give us 54. 3 cubed is 27, so that means we took 2 and 3 to make the 6, and then the rest of them give us the 27. And then similar with the 18, we take 2 of the 3's to make the 9, and then the rest of these will give us 18. So you can get all the divisors from all the possible combinations of the prime factors from the prime factorization of the number, or you could run through this list. So if you're ever unsure if something has those divisors, you can use this technique. Okay, so again, just to recap, prime factorization is writing a number as a product of primes. Okay, of primes. So the primes here we used were 2 and 3. Those were the only 2 primes. We just had lots of 3's, so that's why we got 3 to the 4th using our exponents. Okay, using the product of primes. And then if you're unsure, you go up to the square root of your number. Okay, go up to the square root of your number. So that's why we tested all of these. So that gives you all the divisors, but it also helps you determine if there's even a factor tree or if it's prime. So like if we go back to 41, when we were dealing with 41 before, okay, the square root of 41 is going to be between 6 and 7. My guess would be about 6.5. Okay, just an estimate. Because the square root of 36 is 6. And the square root of 49 is 7. So we know it's going to fall between 6 and 7. So we'd have to test 1, 2, 3, 4, 5, and 6 to go all the way up to the square root. So we know we'd have 1 times 41. It's not even, so 2's out, 4's out, and 6 is out, because those all have to be even. Okay, when we test 3, 1 plus 4 gives us 5, so 3's out, not divisible by 3, and then when we test 5, it doesn't end in 0 or 5, so 5's out. So that means none of these other numbers would work, so the only factors would be this, and again, that tells us it's prime. So it's the same technique, just we use it in a different way to tell us whether something is prime or composite. And you could do the same thing on the other examples we did, either 51 or on 19, same process.